The GSLV Mark III, the third generation GSLV, inherits various technologies from its predecessors. It's very different in terms of its stages, structure, size, and has double the payload carrying capacity than the Mark II version. Nearly 43.5 meter tall and with a lift-off mass of 641 tons, ISRO's GSLV Mark III T2 is about to roar once again at the second launch pad at SDSC Shar.
Geosynchronous Satellite Launch Vehicle Mark III is the heaviest launch vehicle of India. GSLV Mark III is capable of lifting up to 4-ton mass to geosynchronous transfer orbit or a 10-ton payload to low Earth orbit. This vehicle is powered by two S200 solid motors, one L110 liquid core stage and a powerful liquid cryogenic stage C25. This mission is second developmental flight of GSLV Mark III, and this is important mission for GSLV Mark III program, as after the success of this mission, GSLV Mark III will be declared as operational and will join the group of operational vehicles PSLV and GSLV. The payload for GSLV Mark III D2 is a very advanced high throughput satellite GSAT-29, which is a multi-band, multi-beam communication satellite with a lift-off mass of 3.4 ton. GSAT-29 payloads are configured to cater to the communication requirements of users from Jammu and Kashmir and northeastern regions of India. Apart from these operational requirements, the satellite would be demonstrating several new and critical technologies also.
The first stage of this giant vehicle consists of two S200 boosters, which are 26.2 meters long and 3.2 meters in diameter. Each has a capacity of carrying 205 tons of solid propellant. S200 is the third largest solid rocket motor in the world. The L110 core stage carries 116 tons of Earth-storable liquid propellant. It is nearly 21.4 meters long and 4 meters in diameter. It employs two enhanced thrust Vikas engines. The 13.5 meter long indigenous C25 cryogenic upper stage forms the third stage of the vehicle. It uses 28.6 tons of supercooled liquid hydrogen and liquid oxygen, which provides more thrust for every kilogram of propellant burned compared to conventional liquid propellants. On top of the third stage is the spacecraft in the 5-meter diameter payload fairing. The first successful experimental flight of GSLV Mark III took place in 2014 when it carried a crew module as its payload. Both its solid and liquid propulsion stages had performed well, and the vehicle was proven in the atmospheric flight regime. The first developmental flight of GSLV Mark III successfully launched India's high-throughput communication satellite, GSAT-19, weighing 3,136 The GSLV Mark III, the third generation GSLV, inherits various technologies from its predecessors. It's very different in terms of its stages, structure, size, and has double the payload carrying capacity than the Mark II version. Nearly 43.5 meter tall, and with a lift-off mass of 641 tons, ISRO's GSLV Mark III T2 is about to roar once again at the second launch pad at SDSC Shar.
Geosynchronous Satellite Launch Vehicle Mark III is the heaviest launch vehicle of India. GSLV Mark III is capable of lifting up to 4-ton mass to geosynchronous transfer orbit or
Good evening, everyone, and welcome back to Session B of Plenary Session 2 on Middle Atmosphere, Atmospheric Coupling, Dynamics and Climate Change. We will be beginning shortly, and I will again introduce the session chairs, Dr. Kishore Kumar K and Dr. D. Bala Subramaniam from SPL. A word of caution again to all the presenters. During your presentation, if you get a pop-up on your window which asks you to give control of your desktop, please ignore it or deny the pop-up. And from here, over to the chairs of this session.
Thank you. Welcome back to the session 2 of day 3. Now we are going to the first talk on the anomalous weakening of migrating diurnal tides in the mesosphere lower thermosphere by Prijit from SPL VSSC. He'll be giving the talk from this terminal only. And with this one, this is the last talk in the MLT region. After that one, will be slowly coming down to the stratosphere. Over to Prijit.
Thank you, Chair. Can LOC confirm whether the slide is visible or not?
Your slides are visible, sir.
Thank you. Good evening, all. Myself, SS Prijit from SPL VSSC ISRO. I'll be presenting the study on the anomalous weakening of migrating diurnal tides in the MLT region on behalf of both of the co-authors. So as we know, the major excitation mechanisms responsible for the generation of solar thermal tides in the Earth atmosphere includes absorption of IR radiation by water vapor, mainly in the troposphere, absorption of UV radiation by ozone in the stratosphere, and absorption of radiation by ozone, including the EUV absorption by oxygen atoms up in the thermosphere. So in this study, we mainly examine the changes in diurnal tidal characteristics over Tumba. As you know, it is a near equatorial station around 8.5 degree north. And we also examine the causative mechanisms responsible for the anomalous changes in tidal characteristics which we have observed over this region. So this study has been carried out using the measurements of winds, both zonal and meridional components of winds in the MLT region, for a period of almost 10 years from 2006 to 2015, using the SkyMet Meteor Wind Radar. You can see the specifications of the radar system which has been used for the measurements of winds in the MLT region over Tumba. So it is operating at a frequency of 35.25 megahertz, and it gives the measurements of winds at a temporal interval of 1 hour. So using these measurements, we have extracted the characteristics of tides and of course other waves also, using the harmonic analysis by employing the least square best fit method and also the Fourier analysis. So in this figure, you can see the monthly mean values of diurnal tidal amplitudes at different altitudes of the MLT region from February 2006 to December 2015. So here we can see the well-known semi-annual pattern of diurnal tides, with its maximum happening in the periods of equinoxes and minimum at the solstices. So from this, we have tried to see the changes which is happening in the tidal characteristics. So here, this figure actually showing the anomaly, monthly mean anomaly of diurnal tidal amplitudes at different altitudes in the MLT region. So here, the monthly mean anomaly is computed with respect to the mean value of the same month for the 10-year period. So here the positive values are actually indicating the enhancement or strengthening of the tidal amplitudes, and the negative values are showing the weakening of that. So here 2 years or two specific things which we can observe here is the anomalous weakening of diurnal tidal amplitudes in 2010 and in 2012 in January-February period. And in 2010, in fact, the decrease in amplitudes of diurnal tides is going even above 30 meter per second at some altitude levels. But in 2012, it is less than 20 meter per second. So to examine or to see the causative mechanisms which are responsible for this anomalous weakening of diurnal tides in the MLT region, first we have seen the prominent periodicities existing over here during these periods. Here you can see the Fourier spectrum of meridional winds during the period of almost 3 months from 15 December to 15 March, which includes this anomalous behavior or anomalous weakening events which we have seen earlier in these 2 years, 2010 and 2012. So in both the figures, we can see the prominent periodicity at 24 hours showing the persistence of diurnal tides over this region. And the most interesting thing what we can see over here is the occurrence of quasi 2-day waves with periodicity around 48 hours in both the cases. And you can also see that when this strong quasi 2-day wave occurs, the weakening of diurnal tide is happening. The amplitude of diurnal tide is getting weakened. So to examine this in detail, we have seen the day-to-day variations in the amplitudes of both tides and quasi 2-day waves at 91 kilometers altitude level. So here the blue curves represent the day-to-day variations of the amplitudes of diurnal tides, whereas the green one represent that of quasi 2-day waves. The top figure is for the year 2010 and the bottom one is for the year 2012. And the shaded portion is actually representing the time period of those two events, where you can see the amplitude of quasi 2-day wave is more than or larger than that of the diurnal tides. And you can see when it is going to the maximum of quasi 2-day wave amplitude, the diurnal tides are getting decreased. So this gives an indication that the weakening or the anomalous weakening of diurnal tides, which we have seen in 2010 and 2012, may be due to the presence of the quasi 2-day wave events which we have seen, because both are occurring concurrently. And if that is the case, one major mechanism that can lead to this weakening is the generation of secondary waves due to the nonlinear interaction between tides and quasi 2-day waves. So to examine that, we have seen the variations in amplitudes of quasi 16-hour wave, which is one of the secondary waves which can be generated due to the nonlinear interaction between the other two. So here, the first one, the top one is for the year 2010 event, and the bottom one is for that in 2012. So in the second one, in 2012, you can see the day-to-day variations of quasi 16-hour wave is roughly matching with that of quasi 2-day wave. But in 2010, you can see they are not at all matching each other. So here in second case, in 2012, this gives an indication that there is a nonlinear interaction between tide and quasi 2-day wave, and that is giving to the causing the generation of quasi 16-hour wave at the expense of tidal energy. So that is leading to weakening of the tide. So to examine it in detail, further we have seen the changes in phases of these two waves, tides and quasi 2-day waves. So this is for the year 2010. The top one is for tide and the bottom one is for the quasi 2-day wave, and the black curve shows the daily values of phases of both of them, and red one is the 10-day running average of the same. So here you can see the event period, that is between the vertical dotted lines. There is a drastic change in phases of both of them, both tide and quasi 2-day wave. But if we see the same thing, that the variations of phases of quasi 2-day waves and tides in 2012, they are relatively stable. So this stable phase during the event And the generation of COSY 16-hour wave, or the matching between the COSY 16-hour wave and the COSY 2-day wave amplitudes, gives a confirmation that the weakening of anomalous tides which we have seen in 2012 event is due to the nonlinear interaction between tide and COSY 2-day wave and subsequent generation of COSY 16-hour wave. But it is not happening in 2010. So to explore it further, we have we tried to see the changes in the background winds. So here in this figure, actually, this shows the anomaly in zonal winds. So the top one is for the year 2010, and the bottom one is for the year 2012. So here actually this anomaly is taken with respect to the mean value during the same period of 3 months, which is shown over here from December 15 to March 15. So positive values shows the regions where there is an increase, and negative values shows there is an decrease. So in the first event, here we can see at higher levels of the MLT region, the zonal wind is enhancing. It is showing a positive change. But over the lower regions, it is showing a negative change. So to examine this thing in further, we have taken the mean values of the zonal winds at different altitudes of the MLT region during the event. So here in these two figures, that is for 2010 and for 2012, the blue one is showing the mean profile of zonal winds during the events. And the black one is also the mean one for the same period, but from all the 10 years. So the black one is giving a reference profile, and the blue one is representing the event profile, and the red is nothing but it is difference between these two. So in 2010, we can see from the black profile that the zonal wind is westward in nature throughout the altitude. But during the event, if you see this blue curve, we can see that the westward wind is weakening at higher altitudes. And in fact, it is becoming eastward at some altitude levels. But at lower levels, we can see the westward wind is strengthening. But in case of 2012 event, we can see that there is a westward shift for this blue curve throughout the altitude. So in 2010 event, so there is a vertically alternating change is happening for the zonal wind. It is decreasing at the westward wind is decreasing at higher altitudes, and the westward wind is strengthening at the lower altitudes. So this is giving an indication of the filtration of gravity wave drag from the lower altitudes to the altitudes of MLT region. So if we have a strengthening of westward wind at lower altitudes in the stratosphere altitudes, so it will be encouraging the vertical upward propagation of gravity waves which are having eastward phase. So when such gravity waves with eastward phase reaches the MLT region and getting dissipated, it will be leading to the weakening of diurnal tides over that region. So in short, we have examined the variations in diurnal tidal characteristics over a near equatorial situation Tumba for a period of almost 10 years. And the observation shows two anomalous weakening of diurnal tide events. One is in 2010 and another one is in 2012 during January-February period. And during both of these events, we could see the strong occurrence of COSY 2-day waves. But then the further analysis shows that the causative mechanisms responsible for the anomalous weakening of diurnal tides in these two events are different. In 2010 event, the weakening is happening mainly because of the change in background wind due to the COSY 2-day waves. But in 2012 event, the weakening of diurnal tide is happening because of the nonlinear interaction between tide and COSY 2-day wave, and subsequent generation of COSY 16-hour wave at the expense of tidal energy. So with this, I conclude, and thank you.
Thank you, Prijit, for a very crisp and very clear presentation. Now, as you know that MLT region short-term variability in tides are very important topic. So now the talk is open for questions on the chat box. If there are no questions, we'll move on to the next talk. Thank you, Prijit. Next talk is by K. Raghunath of National Atmospheric Research Laboratory. He'll be talking on initial observations of atmospheric ozone with NIRL dial system. Dr. Raghunath. Yes, sir. We could see your slides.
Yes, sir. Yeah. Good afternoon. So this talk is on the initial observations of atmospheric ozone with NIRL dial system. I will be giving a brief presentation on the technical details and how we have realized the dial system, and then some sample observations we have made by operating the system for a few days. So the system was first thought of to be done with the scientific objective to investigate the role of upper troposphere and the lower stratosphere ozone on the stratosphere troposphere exchange processes over Gardanki, and then also to get the stratospheric ozone measurements. So initially we wanted to make it with a range resolution of 100 to 300 meters, height coverage of 1 to 18 kilometers, but we could subsequently go even beyond that, and then with the time integrations of 4 to 30 minutes. As you know, the system for measurement of O3, there are several other techniques are there, like from ozone sonde and from the Brewer spectrometer, where the ozone measurements are relatively very accurate with the help of the potassium iodide solution in the which is sent along with the ozone sonde. And then the Brewer spectrometer, which is operated during morning to evening, 6 a.m. to 6 p.m. And then we get even better smoothed curve over the height regions up to even beyond the stratosphere. But it will have some limitations, as ozone sonde has to be released as and when it is required to get the profile. And then with the Brewer spectrometer, it is limited to during the daytime. And with the help of differential absorption ladder system, we can operate from 6 p.m. to 6 a.m. and then and it will thus complement the Brewer spectrometer observations also. So this is the major equation, the dial equation. If you see the important part of the equation is how the ozone concentrations are achieved is from the n is equal to the absorption cross section of the two on-off wavelengths which are required when we are selecting two wavelengths. One is at on wavelength, that is which will be absorbed by the ozone more, and then off wavelength which is relatively absorbed in a reduced way. So the ratio between the on to off wavelength, the signal strength between on and off wavelength, and together with the absorption cross section of the ozone at those wavelengths will give an estimate of ozone concentrations. Again, when you are doing with ozone concentrations, there are several other factors are there, like the particle information is required, and then the extinction of air molecules, and then there are some interfering gases are there at that particular wavelength which needs to be accounted into. So once this contribution from the other factors are removed, we will get actual information about the ozone concentrations. So as you see here, this is the absorption cross section of the ozone in the UV region, and then this is ozone O3, and then if you see here, there is a interference from the sulfur dioxide and nitrogen dioxide also here in this wavelengths. This has to be removed. And if we globe the cross section from the 260 to 380 nanometer, which is of important to us. So these are the various wavelengths, that is 266 to 355. 266 will have maximum absorption, and 355 and further will have lower absorption cross sections, and hence will get better signal strength here. So this is an representative profile from Gardanki with the help of ozone sonde and a Brewer spectrometer, which is plotted one over other. This is the kind of values we get from the over NIRL. So the differential absorption ladder system, the important parameters are the selection of the wavelength pair, that is on and off wavelength pair. The on and off wavelength pair, the selection of on and off wavelength pair will decide how much is the sensitivity and accuracy of our measurements. For example, when we are going for measurement in the troposphere, the separation between the lambda on and the lambda off should be very small, like 5 nanometer to 10 nanometers, because there is a particulate interference is there. And when we go for stratosphere, it can be up to 30 to 40 nanometers also, as the particles are low in those height regions. And finally, the ratio of the sigma to the lambda, that is the absorption cross-section to the wavelength, that it decides the figure of merit. So this has to be maximized, absorption cross-section to the wavelength which is selected. And then finally, the wavelengths that we are chosen should be available for generation very easily. Energies. So this is a very concise block diagram of the dial system. This is for the off wavelength about 308 nanometers, and then for the generation of 266 nanometers, we are going for the fourth harmonic of the YAG laser. And then the scattering from the atmosphere is taken from the two telescopes, and then they are combined together with the help of an optical fiber, and then give and take collimating and focusing and collimating optics, and then to IF filter, and then a photon multiplier tube, and then further to the data acquisition unit, which is for photon counting mode. So this is the configuration of the dial system. So we have a transmit axis and receive axis. The separation of these two will decide the at what height the beam divergence and the beam divergence and the field of view will overlap. So this will decide the overlap height region. And for our dial system, it is about 3 to 4 kilometers. So these are the optical fiber bundle which we are using for combining the two output from the two receivers, and then it is combined and then given to the one single photon multiplier tube. And then we will go for the, this is the two Cassegrain type of telescopes, which the help of two optical fibers and then given here. And then here the main important thing is the numerical aperture of the optical fiber bundle should be matched with the F ratio of the telescope. Only then the maximum signal will be combined to the photon multiplier tube. And this we have checked with the actual real-time observations, and we have seen that if you take the two independent telescopes, the input from the two independent telescopes is equivalent to the numerically adding up the two inputs from the optical fiber. And this is the 350M Cassegrain Newtonian type of telescope which we are using, and this is about which has spectral coverage of 200 to 1100 nanometer, and it is maximized at between 250 to 400 nanometers. And then it has a reflectivity of greater than 90%. And the two identical telescopes we are using, and then we are combining it. The reflectivity of the Newtonian type of telescope is at different wavelengths is good enough for us to get the signal strength and to analyze the signal also. And this is the data acquisition system, what we have used here. For photon counting mode, we are using, though it has a capability to go in analog detection mode for high signal. As the signal is very, very low, we are going for photon counting mode. And then we are using a photon multiplier tube, which is very, very sensitive. And then it has a gain of 10 to the power of 5 to 10 to the power of 6. This is the receivers which we are using here, two telescopes, and then there is one data acquisition unit here. And then this is ND-YAG laser with fourth harmonic which we are using, and then an excimer laser to generate the 308 nanometer, that is for generation of on and off wavelength pair. And we have a plan to go for 4 receivers so that we can go for higher height coverages and go for and get better height resolutions. which we are now going for 300 meters. We thought of going for 100 meters and with time integrations of low time integrations. And this is the first observations we got from the dial system, which we did it with a time integration of 8 minutes. So this was compared with the from Sonde, ozone Sonde measured ozone concentrations. And this is the mean profile in the month of November, and then with a standard deviation of this one. And with the time integration of 8 minutes, we could go up 22 kilometers here. And we have increased the time integrations up to 30 minutes, and the range resolution of 1 kilometer, and we could go up to heights of 32 kilometers, and from down from 10 kilometers to 32 kilometers. What we are observing is when the O3 concentrations are high, maximum, there is a fluctuations in the observations with the differential absorption ladder system. So this we are looking at now, why the fluctuations are happening here in this, and when the O3 concentrations are very high. So, and again, this is a mean profile taken in the month of September, and with a standard deviation during that month, particular month. So the preliminary profiles are encouraging, and we are planning to do a systematic validation and calibration by taking up various wavelength pairs. Actually, the accuracies and the sensitivity will depend upon what wavelength pair we are choosing. Now we have chosen the two wavelength pair as 266 and 308. We plan to go for 308 and 355 also in the future. And we have taken up the upgradation for the next phase for adding 2 more 350 mm telescopes, so that we can get height coverage of 40 kilometers with better time integrations and range resolutions. And to conclude, so we have got some first observations of atmospheric ozones with the dial system. And is encouraging, and we plan to do for more such observations whenever the opportunity is there, with the simultaneous ozone sonde and dial system operations. And the dial system needs calibration, which we are doing now for any particular wavelength pair. Thank you.
Thank you very much, sir. And we are very happy to know that dial system is shaping up very nice, and initial results are very encouraging. All we middle atmospheric community look forward for this kind of a development. Now the talk is open for a couple of questions.
Sir, this is Raman.
Yeah, go ahead and ask question.
Yeah, sir. May I know what is the energy input energy you are using, sir?
For 266 nanometer, we are using 120 millijoule, okay. And for 308, we are getting 400 millijoule.
Okay.
Yeah, sir. There are 2 questions from chat box. One by Dr. Ramesh. He is asking, I am curious to know why only biaxial system preferred instead of coaxial system for better SNR. Any whole night measurement to see a perturbation in O3 is asking. Total night whether observations are made.
Sir, we have made some initial observations. We have planned to go for full night observations. And we also have planned to continuously observe from evening 6 p.m. to next day morning 6 a.m. But now we wanted to first cross-check whether it is comparing well with the other techniques. Yeah. And now, when we go for coaxial system and biaxial system, we are going for four receiver system. In which case it will be at the center. So when we go for 4 system, it will become coaxial actually. Okay. And then the returns also from the very close by will be very high. Yeah. It will be saturating the receivers also.
One more last question by Dr. Siddharth. If you increase the time integration to 3 hours, whether the height coverage increases? It is also surprised to see the fine fluctuation in dial as compared to the ozone sonde. It is a very good one, like that is telling. Increasing, if integration time is made 3 hours, whether height coverage will be increased, like that asking.
height coverage will be increased, but we have to see if there are any fluctuations, if there is any O3 fluctuations are there within the time period.
Okay, sir.
So that somebody has to tell what is the actual optimum time integrations.
Okay, sir. Thank you, sir. Thank you very much for your nice presentation. Now we are moving on to the next presentation by Dr. Roja Raman from Satyabama Institute of Science and Technology, and he'll be talking about performance characteristic of single cell Raman gas mixture for dial ozone LiDAR. Dr. Roja Raman.
Yes, sir, I am present here. Is my slides are visible, sir?
Yes, yeah. You can make it a full screen, to the full screen. Yeah.
Yes. Now is full screen, sir?
Full screen, but last slide is shown. Summary is shown. Yeah. Go ahead.
Yes, sir. Yeah. Good evening, all of you. This is Roja Raman, presently working at Satyabama Institute of Science and Technology, Chennai. Actually, this talk is related to the previous talk presented by Dr. Raghunath sir. Whereas our aim is to design and develop a portable dial system for tropospheric ozone profiling. So in any case, the most difficult part is the generation of the two wavelengths required for the probing of the particular gas species. So that part I am going to present here, where we will be using a single Raman cell filled with a mixture of gases, and high energy laser is input through the Raman cell. So yeah. So what is the need for this is, as you can see, any gaseous species in the atmosphere, it will have a strong absorption band in particular wavelength in the atmosphere. So in order to observe or measure that particular gaseous species, it is necessary to use the particular band of wavelengths to probe that gaseous species profile. So the most popular technique is the differential absorption technique, differential absorption LiDAR technique, which was proposed for the first time in 1964 by Scotland, and where this dial technique uses transmitting two wavelengths within the absorption band of that particular gas of interest. So the out of these two wavelengths, one will be strongly absorbed by the gas, and the other wavelength will be weakly absorbed by the gas. So when we transmit these two wavelengths, obviously we will get weaker backscatter power from the on wavelength, that is strongly absorbed wavelength, and the stronger backscatter power from the weaker wavelength, that is off wavelength. So by taking the ratio of these backscatter power along with other system parameters and some atmospheric corrections, we can get the number density profile of that gas species. So here our interest gas is the ozone, and this is the total absorption spectrum, absorption cross section of this ozone at room temperature, measured with different techniques. So you can see the strongest absorption is in the wavelength range of 285 to 305 nanometers, especially for the ozone profile in the troposphere. So the experiment is such that we have to choose a couple of wavelengths within this absorption band. One will be strongly absorbing and the other will be weakly absorbing. But these couple of wavelengths are not readily available commercially in the conventional LiDAR system, laser systems. So the technique we can use is the stimulated Raman scattering technique to generate the required wavelengths within the band of a couple of wavelengths within the band of this ozone spectrum. So these are the different Raman active medium we can use in the Raman cell to generate the first stroke and higher order strokes that we can use for the probing of this ozone profile. So where this stimulated Raman scattering uses a strong laser beam will be passed through a Raman cell filled with high pressure Raman active medium, where the high energy laser will interact with the Raman active medium, and higher or lower order frequencies of the laser wavelengths will be emitted. So this we can use for profiling the ozone. But the necessary condition is that, as Raghunath sir was mentioning, the necessary condition is that the differential, the ratio of the differential absorption cross section to the differential wavelength should be maximized. And the another condition is that for especially for a tropospheric range, the difference should be at least 2 nanometer difference, so that it will be spectrally differentiated. The backscatter signal can be spectrally differentiated, and it should not be too long, so that it will not fall into the absorption spectrum of the other gaseous species. So to achieve this one, usually the another important parameter is the interaction length, so that it will have better performance, better conversion efficiency. For that, people use longer Raman cells of 2 meter or greater than that for high altitude ozone profiling. But because our aim is to design a portable LiDAR system, we have to optimize the length of the Raman cell as well as the other optical configuration also. So this is the block diagram of our experimental setup, where a frequency quadrupled laser light emitting 266 nanometer will be used, and the other wavelengths will be terminated using the dichroic prism and the damper, and the emitting wavelength will be 266, purely 266 nanometer, that will be reflected with UV grade mirrors M1 and M2, and this will be focused to the center of the Raman cell using a double convex UV grade double convex lens. And after focusing, the laser light will interact with the Raman active medium in the cell, and the emitted wavelength will have the required set of wavelengths, and that will be collimated using a planar convex lens, and then the collimated beam of laser will be focused to the spectrometer for recording and further analysis. And this is the gas tank where we will input the mixture of gases or the single gas. So this is the actual setup fixed on the optical bench, where initially, before starting the experiment, what we have to do is the Raman cell should be kept open, and a pure, that is more than 90% purity nitrogen gas should be purged through this Raman cell to clear the contaminations, dust contaminations and other gaseous species present in the cell. Then we have to seal this window with seal this Raman cell with UV grade optical windows, and then fill the gas, either single gas or mixture of gases. Then after that only we have to pass the laser beam. Otherwise, the optical windows and the optics will be damaged. Yeah. This is the laser input laser observed with the spectrometer. This is 266 nanometer and only 266 nanometer. No other wavelengths are present. This 266 nanometer will be passed through the Raman cell, and after passing through the Raman cell and interacting with the Raman active medium, these are the wavelengths that will be generated, and you can see nicely see the Stokes on the right side and anti-Stokes lines on the left side, with corresponding to different gaseous, Raman active medium. So from this we can estimate the conversion efficiency using this formula. This is the intensity of that particular Stokes line to the ratio of intensity of this particular Stokes line to the intensity of the input laser 266 nanometer multiplied by 100. This is the simple estimation of the conversion efficiency, and using this we have estimated the conversion efficiency of individual gases as well as the mixture of gases. So this is first we have estimated the conversion efficiency of independent gases, that is hydrogen, which will generate 299 nanometers. So when we started doing the experiment with slowly increasing pressure up to 3 bar, 3-bar total cell pressure, there was no excitation happened and there was no strokes or higher order strokes were observed. From 3-bar onwards, we can see the intensity of the strokes and higher order strokes were keep on increasing. And when we estimated the conversion efficiency of these strokes and higher order strokes, the first strokes is the our interested wavelength region, and this is the conversion efficiency of the 299 nanometers, where you can see the highest conversion efficiency is observed around 12 to 14 bar. Then we have removed that hydrogen mixture and again purged with nitrogen, and then closed the window and filled the methane gas now. And compared to hydrogen, the methane was starting excitation and emitting the Stokes lines from 10 bar onwards. Up to 10 bar, there was no Stokes lines observed. So this is the conversion efficiency starting from lower pressure, and when slowly increase the pressure, the highest conversion efficiency was observed about 18 bar, and whereas the higher order strokes were decreasing. So this is the suitable pressure when we use the single methane alone. So anticipating this, so obviously if we use independent gas mixtures, we have to use 2 cells, and it will increase the optical configuration and the space also. So obviously our requirement is to use a single cell to generate the 2 wavelengths. Anticipating from the previous independent gas results, we have filled the cell with 20% of hydrogen, because as you can see here, with lower pressures, the hydrogen was giving Stokes and higher order Stokes lines, and methane was giving from 10 bar. So with this anticipation, we have filled lower volume of hydrogen and higher volume of methane, and we thought that with this mixture, it can give very good conversion efficiency, means the 289 and 299 both can be observed at a particular pressure level. But surprisingly, what happened, even at starting from 1 bar to about 30 bar, there was no hydrogen excitation observed. Obviously, we don't know the exact reason behind this, and that has to be investigated further. Anyway, because there was no 299 nanometer observed here, we have given up this configuration, that is 20% hydrogen and 80% was given up. So then we filled the cell with 50-50%, that is equal ratio of the hydrogen and methane.
Dr. Raman, you have 2 more minutes to conclude.
Yes, yes, sir. We have started the observation with different pressure levels, and at 20 bar, we could able to see the equal intensities of 289 and 299 nanometers, which were actually required for our purpose. And this is the conversion efficiency of mixture of gases with single cell at different pressure levels, and at 20 bar, both the wavelengths were having equal intensities. And also we checked the mixture of gases with adding buffer gases like helium and argon, and obviously helium was helping little bit to decrease the higher order Stokes, because we don't need the higher order Stokes, we have to suppress that higher order Stokes. So finally we have achieved, we have designed one single Raman cell and optimized the optical configuration to produce a single beam of 288 and 299 nanometers excited with quadrupled NER laser pulse, and the conversion efficiencies at different pressure levels and different gas combinations were observed with addition of buffer gases also. And obviously altogether the mixture of gases with equal ratio, that is 50-50% ratio with addition of helium buffer gas, could help to give better optimal conversion efficiency of 288 and 299 nanometers that can be used for dial ozone layer profiling. And the precaution is that this is very highly sensitive for the gaseous, small changes in gaseous mixture as well as the optical configuration. So this system has to be rugged, and very much care has to be taken if we want to use this system. Thank you.
Thank you, Dr. Raman. It is a very rare to see that Dr. Raman talking about Raman effect. Now it is open to the questions. Yeah. From Dr. Ramesh, there is one question. Is there anything to do stability of Raman cell? Temperature stability.
Yeah, it is highly, as I said, it is highly sensitive. We have to use a controlled chamber when we are using this in outdoor or anywhere. We have to use a controlled temperature chamber, especially for the Raman cell, to have a constant temperature. Otherwise, a small change in temperature will also change the conversion efficiency.
Yeah. Okay. The one more thing. Now there is no more questions. This instrument is available at your institute or it is in Taiwan?
No, sir. This work I have done in Taiwan.
Taiwan.
Yes.
How much, if it is that you wanted to make it here, how much it will be costing roughly?
Roughly, it will cost about 1 crore, sir.
Okay. So if there is
Yes,
no
because,
further questions, let us. I will thank Dr. Raman.
Thank you, sir.
Yeah. Now we will move to the next talk. Now stratosphere is completed. First day we start with F layer, E region, MLT. Now stratosphere is over. Now we are going to troposphere and lower stratosphere. Next talk is by Dr. Sneha Susan Matthew from SPL VSSC, and she'll be talking about Hadley cell dynamics in IATM Earth system model evaluation using ERA5 reanalysis. Over to Sneha. Yeah.
Thank you, sir. Can you please confirm if my slides are visible or not?
Yes, Sneha, it is visible. Go ahead. Yeah.
Okay. Good evening, everyone. Today, I'm going to present my work on the Hadley cell dynamics in IATM Earth system model and its evaluation using ERA analysis. So basically, this is going to be the outline of my talk. I'll be introducing the phenomena of Hadley cell expansion, and I'll be going into the scientific rationale and objectives of the present work, in which I'll be comparing the Hadley cell parameters from IATM Earth system model with ERA5 reanalysis, and a future projection of trends in Hadley cell parameters from IATM Earth system model, and finally the conclusion. Now, differential heating of the Earth's atmosphere by solar radiation causes an increase in energy of the tropics over the tropical regions and a deficit over the polar regions. And in order to redistribute this meridional gradient in temperature or the energy that is acquired, atmospheric general circulation develops, and the part of the general circulation over the tropics in which air parcel rises over the equatorial region, reaches up to the tropopause, spreads out towards the polar regions, subsides roughly over the subtropical regions and move back to the tropics to complete the so-called Hadley circulation. So regions under the ascending branches of the Hadley circulation are characterized by a wet climate, and those under the descending limbs are characterized by a dry climate. And in fact, most of the Earth's major deserts are located under the descending limb of the Hadley circulation. So recently, it has been identified that changes are occurring to the Hadley circulation, especially its descending regions. And according to the 6th assessment of IPCC report, the Hadley cell expansion has been found to be at the rate of 0.5 degree latitude per decade, which is quite significant. And this has got important consequences, especially with respect to changes in precipitation patterns. The established precipitation patterns over the arid regions in the subtropical regions and semi-arid regions, extratropics, pose a major threat to food security, urban settlements, and biodiversity over those regions. Hence, it is necessary that future projections are required from the perspective of formulation of adaptation strategies. And general circulation models or climate models are a major boon in this regard. And IATM Earth system model is the first climate model from India, and it is the general circulation model that is tailored to well represent the atmospheric phenomena for South Asian region. which falls within the tropical ascending branch of the Hadley circulation. It is an improvised version of the NSUB CFS V2 model, and it has a resolution of approximately 200 kilometers. And it is the first model from India to participate in the Coupled Model Intercomparison Project, CMIP6, and the IPCC 6th Assessment Report. And being in addition to the Coupled Model Intercomparison 6, Phase 6, it is necessary that it has not gone into the previous studies on the Hadley cell expansion using climate model simulations, and hence it is necessary that this particular model be evaluated for its efficiency in representing the Hadley cell dynamics. And in the present study, I use the IITM Earth System model. I try to evaluate it, and for this I use basically the meridional wind data from historical runs and two projection runs, that is SSP 370 and SSP 585. Both are two high forcing scenarios in the CMIP6. So these are my objectives. I will try in the present work. I am trying to delineate the Hadley cell edges from IITM Earth System model using the meridional mass stream function metric, and the Hadley cell edges and center is obtained and compared with that from ERA5, and the evolution of total width of the Hadley cell and its ascending regions is compared against the time series for the ERA5 reanalysis. And finally, I try to make future projections in the ascending and descending branches of the Hadley circulation under two high forcing scenarios using the model. And this is a comparison of the meridional stream function from IITM Earth System model and ERA5 for boreal winter and boreal summer season. And it can be seen that the IITM model and the ERA5 reanalysis are in close comparison with each other. This is the center of the Hadley circulation during DJF season, and these are the edges, and the latitude of maximum stream function, which you can observe here, are the edges of the ascending regions, or here from here to here, this is going to be the ascending branch of the Hadley circulation, and from here to the edge, this is the descending branch of the Hadley circulation. So there is, it can be seen from this figure that there is close match between the model and the reanalysis, and an annual cycle for the Hadley cell parameters. A comparison between them has been done for each of the Hadley cell parameter and the total width of the Hadley circulation, and it can be seen that here also there is close match between the model and the reanalysis, and in representation of total width there is a slight underestimation, but overall the annual cycle is having a good match. And the changes in the width of the Hadley cell ascending and descending regions were explored into, and this is these are the plots for anomaly in total width and total width of the ascending regions and total width of the Hadley circulation. And it can be seen that the evolution of the Hadley circulation as given by the model and as given by the reanalysis are in close agreement with each other, with a few exceptions which we expect. And keeping in mind of the discrepancies and the overall agreement between the model and the reanalysis, we go forward to project the dynamics of the Hadley circulation into the future in the presence of two high forcing scenarios, and these are the results. And here I am identifying the annual cycle of the trend in width of the regions, and that for the total width of the Hadley circulation for the northern hemisphere and southern hemisphere separately, so that I can bring out the asymmetry in the trends happening over the northern hemisphere and southern hemisphere separately. And it can be seen from this figure that there is large hemispheric asymmetry, with the southern hemisphere showing larger expansion as compared to northern hemisphere, And it can also be seen from these figures that there is all throughout the year, there is an expansion of the Hadley circulation, ascending and descending regions, both shown in the southern hemisphere. And whereas in the northern hemisphere, the case is a little bit different. It shows the SSP 370 projections. They show basically a contraction during the summer months and an expansion during the winter months, which is slightly like northern hemispheric descending regions undergo an expansion during boreal winters months and a contraction during summer months, and the ascending regions, for the ascending regions, the expansion or the trends are remaining either the same for the SSP 370 scenario or contract during most of the year. And these are my conclusions. So I have tried to delineate the boundaries of the Hadley circulation ascending and descending branches for the northern hemisphere and the southern hemisphere. And this is for the first time that the Hadley cell boundaries in ascending regions and their future projections are delineated, and the future projections are made for the first time. And present study, I have compared the Hadley circulation representation by the IITM Earth System model and the reanalysis, and showed that the model is able to reproduce the structure and intensity of the Hadley circulation. And the ascending regions and descending regions delineated from the model is found to fairly agree well with the boundaries obtained using ERA5 reanalysis, and especially in the southern hemisphere. And future projections of the Hadley circulation ascending and descending branches up to the year 2100 show that there is significant expansion of the regions in the as shown by the model in the southern hemisphere, and whereas a contraction is shown in northern hemispheric Hadley cell during summer, and an expansion during the winter months. It can be it is brought out that the projected expansion of the Hadley cell will be the expansion of the southern hemispheric Hadley cell, including its ascending and descending region boundaries. Thank you so
much. Thank you, Sneha, for a very crisp and clear presentation and scaring us with the future projections. Now the talk is open for questions. Yeah. There is a question from Venkatratnam.
Yes.
Is it possible to see whether any change in Hadley cell during COVID lockdown?
Changes, actually, when we are speaking about Hadley circulation changes, we are calculating trends as per the decadal trends we are looking into. And so COVID-19 lockdown effects means it's only 1 to 2 years maximum, or a seasonal 3 to 5 months, or maximum to the maximum of 2 years. So it is, I don't think this trend analysis will be suitable for projecting or for identifying the effect of lockdown on Hadley circulation. I don't think the data, the time span will be suitable.
Okay, and next question is from Dr. Ramesh. Do this model is open source?
It is open source. It is actually CMIP6 is a platform where the climate models from climate model outputs from different countries are available on a single platform, which is available for comparison, for intercomparison, and outputs are also available open source. So
no, Dr. Sneha is asking whether model is open source, not the output. Model is open source.
No, actually, I have used the CMIP6 output given by the model to the CMIP6 platform. So this model, they are providing it on the open source platform.
Good. One more question from Dr. Nirvikar. How do the changes in Hadley cell propagate upwards? Upward means in the stratosphere and mesosphere.
as of now, studies are going on how this on the interaction between the Hadley circulation and the upper layers of the atmosphere. I mean, stratosphere and mesosphere. So it can the ascending branches of the Hadley circulation has we can expect that some amount of this upwelling is reaching up into the stratosphere also. So we can expect that the changes are occurring into the stratosphere also, but it is yet to be explored. This is a field where people are right now trying to explore into. Studies are going on.
Okay, Sneha. If there are no more questions, thank you, Dr. Sneha. And
Yes,
now
sir.
we move on to the next talk. Next talk will be by Dr. Sandhya from Providence Women's College, Calicut, and she'll be talking about influence of Southern Hemispheric upper troposphere PV intrusion events on the Southwest Monsoon Region, SWMR. Over to Sandhya.
Thank you, sir. My screen is visible.
Yeah, it is visible. Now you can go to the full screen mode.
1 minute. Okay, sir.
Now maybe it may be taking time. I don't know. It's still not in full screen mode.
Ma'am, could you try sharing your entire screen? I think you are just sharing your presentation window. Can you stop sharing and try again?
Okay.
When you share first thing, you make it the desktop whole.
Okay, sir.
Yeah. Now open your presentation. Yeah.
Okay, sir.
Yeah. Okay. Now go ahead.
Yeah. Good evening, all. Topic of my presentation is influence of Southern Hemispheric upper tropospheric potential vorticity intrusion events on the Southwest monsoon rainfall. When Rossby wave breaks at mid-latitude, which leads to the intrusion of stratospheric air with high PV into tropical troposphere. This stratospheric air can be identified in the troposphere with a PV value greater than or equal to 1.5 PVU. This PV intrusion normally triggers convection to the east as a result of decreased stability and enhanced upward motion ahead of intrusive trough. Vo and Polvani studied the climatology of PV intrusion at 10 degree north and 10 degree south. And they observed that the PV intrusion events are more frequent over Pacific region, followed by Atlantic sector during winter months, whenever the equatorial westerlies are strong. And we have studied the climatology of PV intrusion over Indian sector. And we have found that though the PV intrusion events are less compared to Pacific and Atlantic sector, these events are happening over Indian sector also. However, unlike Pacific and Atlantic sector, more intrusion occurs during pre-monsoon months over Indian sector. From the lower panel, you can see that. And one more thing, there is no PV intrusion at all during Southwest monsoon month from June to September due to the existence of tropical easterlies. However, though there are no PV intrusion events occur over Northern Hemisphere, the PV intrusion events are frequent over at Southern Hemisphere during the same time. And from this figure, you can see that the blue line plot represents the interannual variability of PV intrusion events at 15 degrees south latitude, 0 to 90 degree east longitude. And the bar graphs represent the time mean removed rainfall during June, July, August, September month during southwest monsoon rainfall. And it can be noted that whenever there are more PV intrusions, it coincides with less rainfall most of the cases. So in order to observe the relation between this southern hemispheric PV intrusion and southwest monsoon rainfall, we have selected some years with positive and negative rainfall. And in this figure, 2 years are shown, 1994 and 1986 are shown. And the top panel, the year 1994, is an El Nino year, but it is an year with a positive rainfall anomaly. And we can see from the top panel that there are very less number of PV intrusion events occur during 1994, especially during the first 3 months of the monsoon period. And it can also be noted that though there are some PV intrusions during June and July months, the spatial extension of that PV intrusion events are less than 5 degrees and they last less than 2 days. And moreover, the majority of the intrusion is restricted to 0 to 20 degree east and which may hardly impact monsoonal flow. The lower panel shows the year a PV intrusion or the PV plot for the year 1986. And the year 1986 is a negative rainfall anomaly year, though it is an ENSO neutral year. And we can see more number of PV intrusions during 1986 when we compared it with 1994. And out of these PV intrusions, almost majority 5 events occur during June and July months. And the spatial and temporal extension of these events are more than respectively 10 degree and 5 days. So how does a PV intrusion can lead to break in monsoon? The low level Finlater jet carries both moisture and negative PV from southern hemisphere to northern hemisphere. If significant negative PV get into northern hemisphere, it can lead to instabilities, and this leads to strong southward turning of low level flow so that air tends to avoid Indian sector and even turn back to southern hemisphere. So this may have serious consequence in moisture flux to India and therefore to monsoonal rainfall itself. To check the theory proposed by Rodwell, we have selected a day in 1986. We have selected 3rd July, which is a peak intrusion day, and we have checked the height longitude plot of PV, and we can see that the PV descends from around 100 hectopascal and it reaches around 700 to 750 hectopascal, that reaches even very lower level. So this low level might have to see whether this low level PV influenced the wind pattern. We have plotted the wind vector at 850 hectopascal on 3rd July 1986, and the rectangular box you can see a clear overturning of the wind at the lower level. And this low level overturning of low level flow associated with high PV event might have led to break spells in monsoon. Krishnan et al. Identified the break spells in southwest monsoon from positive OLR anomaly over northwest and central India, provided the average OLR anomaly over 73 to 82 degrees east, 18 to 28 degree north exceeds 10 watt per meter square. And we have adopted the same criteria to identify the breaks in monsoon And we observed that the table shows the Euler anomaly for some days before intrusion and some days after intrusion. And the red letters marked the intrusion days, and it shows clearly the Euler anomaly is greater than 10 watt per meter square, and which represent a break spread. So, in order to express the relation between this southern hemisphere PV and southwest monsoon rainfall quantitatively, we have done temporal correlation, and it shows a significant negative correlation between southwest monsoon rainfall and southern hemispheric PV events. From the year 1999 onwards only, we are not getting any correlation, significant correlation before that. From 1999 to 2018, it significantly correlates negatively with southern hemispheric PV intrusion events. So in summary, the present study confirms occurrence of more PV intrusion events at 15 degrees south over 0 to 90 degrees east, which coincides with a negative rainfall anomaly during southwest monsoon period. And the temporal and spatial extension of PV intrusion events are respectively more than 3 days and 10 degrees when it seems to influence the rainfall. And the PV intrusion events shows a significant negative correlation from 1999 onwards. And the PV intrusion events at southern hemisphere versus the monsoonal, low-level monsoonal flow from north to south during the next day of PV intrusion or during that day of PV intrusion itself. And this might have contributed towards the less moisture transport and breaks in monsoon, and hence negative rainfall. Thank you.
Thank you, Dr. Sandhya, for crisp and clear. I think some echo is coming. Hello. No.
Yeah.
Thank you, Dr. Sandhya, for crisp and clear presentation. And you have shown that the intrusion of PVs over southern hemisphere around 15 degrees south has a correlation with our Indian summer monsoon. Now the talk is open for questions. There are no questions in the chat box also, and there are no hands raised. So now we'll move on to the next talk. Next talk is by Dr. Hemant Kumar from National Atmospheric Research Laboratory, Gadanki, and he'll be presenting an overview of the vertical distribution of UTLS chemical composition over Asman. Dr. Hemant Kumar.
Yeah, good evening, sir. Am I audible?
You are audible, and your presentation is nicely seen. Yeah, you can go ahead.
Thank you, sir. Firstly, good evening to all. I'm Hemant Kumar from NARL. I'm really thankful for giving me this opportunity to present an overview of the vertical distribution of the UTLS chemical composition over Asian summer monsoon anticyclone. The Asian summer monsoon anticyclone is a large-scale anticyclonic circulation in the upper troposphere and lower stratospheric region extending from Western Africa to Middle East with a vertical extent ranging from 300 hectopascal to 70 hectopascal. This circulation is mainly formed as a response to the intense heating of the Tibetan Plateau and also the latent heat release that is associated with the deep convection which is persistently present during this season over the South Asian region. And the most importantly, the strong westerly winds on the north and easterly winds to the south makes this circulation unique by trapping and confining several radiatively active chemical species and aerosols which have severe climatic implications. So this is an example that I've collected from Park et al. 2007 and Werner et al. 2018, where it shows the confinement of the tropospheric species, particularly CO, in the Asian summer monsoon anticyclonic region, water vapor and aerosols, and a decrease in ozone is seen in the same Asian summer monsoon anticyclonic region at 100 hectopascal. However, there are several studies which are now being present addressing the variability of different chemical species and also different aerosol properties of the Asian summer monsoon anticyclone, including its composition. So the variability of the Asian summer monsoon anticyclone is closely associated with the changes in the convection and the dynamics. And any change in the strength of the Asian summer monsoon anticyclone will have impact on the changes in UTLS chemical composition. And several studies were made to address the variability of the Asian summer monsoon anticyclone, particularly during the strong and weak monsoon periods, La Nina and El Nino periods, active and break spells. And at the same time, they have also looked into the distribution, particularly of chemical composition near to the tropopause level. So whatever the studies that were made earlier were all related to the tropopause level only. So in this study, I am going to discuss the variability of the chemical composition, particularly in the vertical direction at subseasonal and regional spatial scales. So in order to address the variability at subseasonal scales, firstly, we need to identify the variability of the Asian summer monsoon anticyclone. For that, we initially need to identify the center of the Asian summer monsoon anticyclone, as any change in the Asian summer monsoon anticyclone center is considered to be the variability of the Asian summer monsoon anticyclone itself. For that, we initially identified the center of the Asian summer monsoon anticyclone over the region 15 degrees to 45 degrees north and 30 degrees to 140 degrees east by following a method adopted from Zhang et al. 2002, where two steps it is involved. There, where the first step is a ridge line is identified first, which means wherever the absolute minimum journal wind is observed in the longitude range between 30 to 140 degrees in this whole range, and once the ridge line is identified, along this ridge line, wherever you have maximum geopotential height, that particular point is considered to be your center of Asian summer monsoon anticyclone. So we have collected the Asian summer monsoon center for all the June, July, August months for the period 2010 to 2018, and we could identify that the variability is having different modes. And the same is represented in the mean picture of the geopotential height obtained from the same period, with horizontal wind circulation clearly visible here. You can clearly see that the Asian summer monsoon anticyclone variability has three different modes, one in 50 to 67.5 degrees east, which is called the Iranian plateau mode, and the other one at 80 to 92.5 degrees east, which is called as the Tibetan plateau mode. And in between these two, there is another mode which is called elongated mode, as it stretches between 67.5 to 80 degrees east. So before looking into the vertical distribution of the chemical composition of these particular modes, initially we tried to see the behavior of these chemical species, particularly at 100 hectopascal, using the satellite observations from MLS. And this represents the mean picture of the chemical composition for the period 2010 to 2008 at 100 hectopascal, where the top is for the carbon monoxide, and middle is for ozone, and the bottom is for water vapor. And the vertical first panel is for the IP mode, and the middle vertical panel is for TP mode, and the last vertical panel is for elongated mode. You can clearly see from in all these things, you can clearly see the tropospheric species, particularly the carbon monoxide and water vapor, shows enhancement in the Asian summer monsoon anticyclone region, and at the same time, the ozone also is showing a decrease. This is the feature of the Asian summer monsoon anticyclone. But however, a shift in the longitude is observed in the IP mode for the enhancement, as you can see, between 50 to 67.5, whereas for the TP mode, it is 80 to 92.5 degrees east, and whereas for the elongated mode, the shift is present in between 50 to 92.5 degrees east. Once we understand the spatial distribution variability, so we need to look into whether if there is any changes in the vertical direction of these chemical species. For that, we obtained the anomalies of the carbon monoxide, water vapor, and O3 for all the different modes, and shown, and the mean picture of the total period, as I mentioned in the previous slide, is shown here. You can clearly see that the tropospheric species, the first two are the tropospheric species, whereas the last is the stratospheric tracer species. You can clearly see that there is an enhancement in the tropospheric species, both in carbon monoxide and water vapor throughout the troposphere, which is clearly seen here. But at the same time, if you see such enhancement is not seen in the case of IP mode, where the lower levels are not having any enhancement, but only the enhancement is seen in the upper levels, that too near to tropopause, 146 and 100 hectopascal. If you see the ozone, there is low concentration of ozone in all the three modes without much variability as seen from this figure. Then we try to look if there are any changes in the vertical direction with respect to longitudes. Then the anomalies are obtained for the latitude region 25 degrees to 35 degrees north, and the mean picture of the anomalies with respect to longitudes is shown here. And similarly, you can clearly see that the carbon monoxide enhancement is seen throughout the troposphere, both in TP mode and elongated mode. At the same time, the water vapor also shows an enhancement in TP mode and elongated mode, but not in the IP mode, where only the enhancement is seen in the upper troposphere and low stratosphere region. So, and one more thing is the enhancement is there in TP mode, which is reaching near to tropopause, which is not present in the elongated mode. And at the same time, the feature of the Asian summer monsoon anticyclone is clearly seen that wherever the variability of this mode is present, low values of ozone are clearly noticed. But however, there is high ozone concentration over the longitudes. 80 to 100 is present in IP and elongated mode, but not in TP mode. So in order to check if this type of variability is seen only during particular modes or any two during particular days, or is there any differences in different regions? So we initially thought we will try to check with different regions how the vertical distribution of these species is going to vary. For that, the total Asian summer monsoon anticyclone is divided into mainly 4 regions, where it is northwest, northeast, southwest, and southeast. So we tried before to check that, we tried to obtain the vertical distribution of the chemical species, and the anomalies are obtained, which is shown in this figure. So where this is CO, and the middle is for water vapor, and the last is for ozone. And this left is the western side of the Asian summer monsoon anticyclone, and this is the eastern side of the Asian summer monsoon anticyclone. You can clearly see, similar to the earlier figures, as we observed in TP mode and EP elongated mode, enhancement in the tropospheric species is seen in the eastern side of the Asian summer monsoon anticyclone, and which well pronounced in the southeast region of the Asian summer monsoon anticyclone when compared to the northeast part of the Asian summer monsoon anticyclone. And at the same time, similar to the IP mode, the enhancement in the tropospheric species is clearly seen only in the near tropopause level, particularly in the western side, but too well pronounced in the southwestern region of the Asian summer monsoon anticyclone. And the clear feature of the Asian summer monsoon anticyclone is seen in the southwest and southeast part of the Asian summer monsoon anticyclone ozone. But however, there is some little changes are observed in the ozone in the northwest and northeast part of the Asian summer monsoon anticyclone. There you can clearly see that there is an enhancement just below the tropopause in both northwest and northeast part of the Asian summer monsoon anticyclone. In order to see what could be the reason for this variability of these chemical species, we try to obtain the difference of the different background meteorological conditions, mainly the dynamical parameters, and shown here, where the top is for zonal wind and middle is for meridional wind, and base is for the pressure vertical velocity. You can clearly see that wherever the high values of CO and water vapor are observed, a clear updrafts are seen. Here negative omega is nothing but strong updrafts are seen in the southeast region, and at the same time a prolonged decrease in the zonal wind is also seen in the southeast and southwest part of the Asian summer monsoon anticyclone, which makes an easy transport of the chemical species which are already available during the emissions that are always present there. And that could be the reason for the observed enhancement in the throughout the troposphere in the case of southeast mode, as I showed in the previous figure. But however, as I mentioned earlier, there was an increase in the ozone concentration, particularly just below the tropopause in the case of northwest and northeast. For that, we looked into the potential vorticity intrusion events, particularly using the ERA interim data for the period 2004 to 2020, and we could easily see that there is a high PUE is observed, particularly over the northwest region and northeast region, which could be the reason for the observed enhancement in the ozone, and due to the more possibility of stratospheric intrusions over that particular region. So in summary, I can in summary of the previous two means things that I have mentioned here, I could clearly say that whatever the available emissions that are present there, and also along with that, the deep convection and the advection will be mainly responsible for the vertical variability of the UTLS chemical composition during different modes and over different regions of the Asian summer monsoon anticyclone. But however, we got a rarest opportunity to check if what could be the role of purely dynamics on the UTLS chemical composition. We tried to look the influence of the COVID-19 lockdown on the UTLS chemical composition, where the top panel, where this is the this represents the percentage difference for CO.
Dr. Hemant, you have 2 minutes.
For 3 different regions, IGP, Central India and South India, we can clearly see there is an enhancement in the carbon monoxide in all the regions, irrespective of the regions. And this enhancement is there even if there are no emissions during the COVID-19 lockdown. And in order to check what could be the reason, we found that the strong updrafts which are present here just before the lockdown and the prolonged decrease in zonal wind which is present there throughout the lockdown period might be responsible for the easy transport of the chemical species which were present there prior to the lockdown. So in summary, I can say that the chemical composition of ASMA shows strong vertical variability at subseasonal and regional scales, and the strong vertical updrafts and background dynamics combined with the surface emissions over the region play an important role in the vertical distribution of the chemical species in the Asian summer monsoon anticyclone. And particularly in COVID-19 lockdown, the dynamics which played a major role in deciding the UTLS chemical composition, though it is of a different season. And finally, whatever the changes that are seen are expected to have an impact on the climate, and so the radiative impact need to be estimated separately instead of considering the total Asian summer monsoon as a single entity. Thank you. And for further details, these papers can be referred. Thank you.
Thank you, Dr. Hemant, for a very good overview on the vertical distribution of trace gases in the UTLS region. It's really very informative and very interesting. Now the paper is open for questions. There is one question from the chat box by Mr. Musaid. He is asking what would have caused for increased anomaly of ozone during elongated mode. Hemant, did you get the question?
Here. Yeah, I'm here. Yeah. So actually, I hear that's what there are so many PV intrusions which are happening on the northwestern, northeastern side, and that could be the reason because the elongated mode shows enhancement, particularly in that particular longitude range, as I mentioned here.
Okay. Any further questions? So I have one question, Hemant.
Sir.
You have done a very good job by quantifying how much variability because of this asthma thing. Whether have you any time computed this radiative forcing because of this trap?
Yes, sir. That's what that work I've started, and actually I'm trying to look into the radiative forcing by considering separate modes over different regions separately.
Yeah, this will be a very interesting to study. Okay, thank you.
Thank you, sir.
Now we'll move on to the next talk. It will be given by Dr. Sanjay Kumar Mehta from SRM Institute of Science and Technology, and he'll be talking about Asian summer monsoon anticyclone and its variability. Dr. Sanjay Kumar Mehta.
Hello. Yeah, hello.
Yes, Sanjay.
Yeah. I'm audible?
Yeah, you are audible.
Yeah,
you have to
thank you.
share
Thank you
your
very much,
presentation.
Yeah. So thank you and good evening to everyone. So I have to share my okay. Is it visible now?
No? You have to show your presentation. Yeah, now it's visible. Yeah, you have to go to full mode, full screen mode.
Because I cannot see here. Okay. Yeah, it's full mode now, full screen
Yeah,
mode now.
yes,
Yeah.
yes.
Yeah,
Go
thank you,
ahead.
sir. Yeah, thank you, and good evening to everyone. So this is the talk which I'm going to give on the Asian summer monsoon anticyclone and trace gases during active and break phases of the monsoon. So the previous talk was similar to that what actually I want to talk here, and I think it is thank to Dr. Hemant that he has briefly talked about that about the asthma. So this is the schematic diagram which I am showing, which will describe about this, what is this asthma and why it is important so to study. So it is showing here that the transport process from the troposphere to the stratosphere, and as you know that the asthma is Asian summer monsoon anticyclone is horizontally confined within the subtropical jet in the poleward side or northern flank, and the tropical easterly jet in the equatorward side. And also you can see that during this Asian summer monsoon, the intertropical convergence zone, ITCJ, that is actually the propagate or moves towards the northern part, and then you see that the low pressure area developed there. And because of that, deep convection actually happen over that region, and that leads to the slow enters of the tracer or the chemically active tracer, for example, the hydrogen cyanide, carbon monoxide, carbon dioxide, and methane, and nitrates. So, as well as the water vapor and the ozone. So here, yeah, this asthma basically actually confined within the convective outflow level that is actually about 12 kilometers to the cold point tropopause altitude region. So from and then that during during monsoon season, actually this the tropopause height also is higher at higher altitude relatively, and that actually leads to the transport to the lower stratosphere. And as we know that the Asian summer monsoon is the dominant the climatical feature of the global circulation that is generally during the northern summer, that June to September, and it is also clear that the origin for this ASM actually lies due to the differential heating at the surface, which is it is shown here. It is kind of the Maslow-Gill pattern, and the force by this Kelvin wave and Rossby waves, and you can see that that leads to the heating. This heating leads to the convergence or the low level pressure areas in the surface level and the high pressure levels at the upper level, about 250 or 200 millibar. And consistent to this one, we can see that we observe actually two high level. That is, one is that what is the anticyclone, and two high level. That one is anticyclone over the Indian monsoon region. And that we have seen that it is because of that the monsoon circulation that actually asthma develops. So now it is actually also known that the convection actually play important role for this variability. Now to how to define that one asthma. So Randall et al. 2006 proposed that to define this based on this the modified potential vorticity. Also he calculated the circulation, and you can see this figure actually demonstrate that how outgoing long radiation, that is proxy for convection, actually correlating with the circulation that is used for the defining the asthma and modified potential vorticity. So from this actually to motivate us that this the asthma circulation actually governed by the convection. Then if this is the case, then there should be variability because of the transient oscillation of the monsoon. That means the active and break phases of the monsoon. And that actually the main objective of this talk. And also, if it is, yeah, and then after analyzing what we have observed that this the asthma during different the phases of the monsoon actually also resemble with the different different modes of the asthma that is already existing or well known. The modes are really actually the Tibetan mode and Iranian modes. And also we have looked into that, how these modes actually vary with the active and break phases of the monsoon. So main data set in this study, what we have used ERA5 and MLS data for the period of 2004 to 2019. So here I am showing that the climatological structure of the geopotential height. Geopotential height we have taken at 150 hectopascal. Many studies have taken at 100 hectopascal, and it is from the Randall et al. It is defined that about 14.32 kilometer geopotential height actually resembles this the circulation, and that is been taken from for the many studies, and that can be identified the asthma. So we calculated that asthma for the active and break phases for the period of 2004 to 2019, and that we have used for this calculation using this active and break phase calculation we have used from Rajiv until 2006, and we have taken the month for that month this July and August. We have not taken June and September. So we consider based on that thing, what we can see here is that top figure here it is showing this is the geopotential and wind circulation, wind and geopotential height is shown, and then the red one indicate the active the asthma for asthma circulation for the active condition, and the blue one for the break condition, and the black one is the mean one. So you can see that there is a significant change between this break to active the phases. The asthma has the significant differences. So, and you can see that the during active case, this asthma circulation is more elongated than the break phase. So what we have shown for the active and break here, that the figure describing. Here what we have shown right side, we have taken the carbon monoxide for the same period, and we have shown that the climatological mean for that one, and also the water vapor and ozone. Now we have taken here the carbon monoxide for the active phase, break phase, and the difference. So this is what we see that you can see very clearly during the active phase that carbon monoxide is more the concentration is there more in the Iranian mode, while in the break phase it is more towards the Tibetan as well as in center of the asthma. So there is a distinct variation can be seen. So when we take the difference, what we see that during the active phase there is a less transport actually happening and that is what we can see that here this negative value of this difference. So active, and it could be the reason why this is less. One is that as we know that the convection will be stronger during the active, but still why it is less. It could be because of that the transport of the clear air, more clear air than the break monsoon, because during the active phase the rainfall will be the more when compared to the your break monsoon, when it is the intermittent rainfall will be there. So yeah, so similar situation is there. We can see there here, for example, and compared to that, when you see this can be actually supported when you see the water vapor transport. So water vapor, we see that during active phase is more when compared to the break phase. That what actually is support the content what we said for the CO. And coming to the ozone have the minimum. So ozone is the minimum again is in the Iranian mode. We can see that Iranian side of that, and during the active phase, and during the break phase it is in the Tibetan side. So this is also indicate here. I cannot see this. So that is the differences between the active and break phases. Again, why ozone is having more minimum there? Again, the same thing supported here. Again, whatever the ozone would have been because of the tropospheric or from the troposphere, then it is the more minimum, lesser more clear air is transporting to the upper troposphere or in the asthma region. So this could be the reason. And then after that, we looked into how we looked into the vertical distribution. There we have focused on the there we focus for the average between the 215 to 100 hectopascal. Here we have looked into the vertical structure. So here we see that which longitude sector actually the more pronounced the transport is there. So we can see here the more pronounced transport in CO is actually from this. You can see that 80 to 100. You can see from here that active minus break. So that again, as the same thing will be there, that during the this 80 to 100, that we have the lesser transport during the active phase than the break phase. So it is same condition is there, that that clear air will be the more during the active phase. But one thing important is that you can see in the stratosphere that the carbon monoxide is more compared to the over the sector 60 to 80 east compared to the 80 to 100 east, where the Tibetan mode is there in the break phase and the Iranian mode in the active phase. So here, though there is less transport of the carbon monoxide in the asthma region, it is more it is transported to the lower stratosphere more during the active case than the break case. So it is also again related to that convection, because convection will be stronger than during the active case than the break case. So the same story goes for the water vapor and ozone. So ozone basically for the water vapor, as you see that more water vapor in the Iranian mode or the active phase that where we have. So that is what we have, and it is supporting also. And for example, for the ozone, it is lesser here. Then to understand in better way, we have also looked into the whether this what we are talking, how this.
Dr. Sanjay, you have 3 more minutes to conclude.
Yeah, thank you. So that we have seen also the vertical the transport we have taken for that the vertical velocity that omega. So this blue indicates the blue, that means blue means negative, indicate the vertical motion, and the red one is the subsidence. So we have that here. You see that as we are discussing already, that during active monsoon we have the more convection, or sorry, more the vertical velocity or the more the vertical motion when compared to the break. So then we can see that there is a 2 sector actually there, 60 to 80, and then about something like that, about 100 to that one in the longitude, and also we have seen for the latitude also. So like that, once we have did that, we understand that the active phase, during active phase, the Iranian mode is more dominating, and then the break phase Tibetan mode is more dominating. That's what we did. We have analyzed several cases, and then we actually seen that this case can be identified based on the dividing that taking this line we have taken at the this 50 to 65 and 80 to that is center to that one. 50 to 65 means about 70. We have taken the line, and then whenever the maximum is occurring, to Iranian side we have taken Iranian mode, and then other side that we have taken Tibetan mode, and when the both sides is there elongated, that we have considered as a bi-mode, and we have taken that one. So like that we identified, and then you can see that there is Iranian mode very clearly seen in the G potential, and we calculated the CO for that thing, carbon monoxide, and we see the pattern here. Iranian mode mostly concentrated in this one, and that is the Tibetan mode is here, and bi-mode throughout this asthma, this circulation. And when we calculated this one for the active and break cases, again, just we are actually it's earlier itself, if we were the interpreting, the results also came the similar way. What we seen that Iranian mode is more during the active condition, and then the break condition, and Tibetan mode is more during the break condition. So that is what. And then Hemant was actually discussing about that the transport of the ozone or the tracer is more during the this Tibetan mode. So could be, could be. I think, we have to think that whether this is in active phase coming. I think Iranian mode coming here is the active phase. So we have to investigate that why the Tibetan mode having the more transport to the lower stratosphere. This is my summary. What we have seen that it can be noticed that the ASMA region has a significant change in the spatial coverage during the active and break condition. During active monsoon days, the ASMA region expands more along the zonal east-west direction when compared to the meridional direction. The concentration of upper tropospheric CO over the Indian monsoon region is more during the active days more during the break days than the active days. It could be attributed to the relatively clean air transport during the active monsoon than the break monsoon condition. During monsoon, during active monsoon days, convection strengthened over the northwest India, central India, and head Bay of Bengal. However, break days are associated with the anomalous convection increase over the eastern side, eastern equatorial Indian Ocean, foothill of India, and central East China and eastern part of India. Enhanced convection over the eastern part of the ASMA region we have seen during the break monsoon days, and might have that contributed to high concentration of CO over the eastern part of the ASMA. ASMA is centered either of the Iranian plateau or of the Tibetan plateau. And we observe that, and it is observed that the Iranian mode occurs frequently during the active phase, while the Tibetan mode during the break phase of the monsoon. So we have to understand now that when the pressure which is in the ASMA and transported to the lower stratosphere, which has the global impact, has to be investigated. Yeah, thank you, sir.
Thank you, Dr. Sanjay, for a very good talk on Asian summer monsoon anticyclone, and you brought out very good distinguishability between the active and break monsoon. I think you are also going to doing more research on finding out what exactly makes this kind of a different distribution of trace gases during these two phases. Now the talk is open for questions. There is a question from Dr. Nirvikar. What are the different reanalysis data sets used for this study? Do you find any difference in context to the ASMA among different reanalysis data sets?
Yeah, thank you. This is a very good question. I think I have not investigated this one, but there are group investigating that different analysis for the how this going to represent differently the ASMA region. So, but I have used here only ERA5 data, but there are some differences among the reanalysis products are there, and that research I think it is undergoing. I have not seen till now the publication, but there are differences among them. But yeah, what is that we have to see the unified result, means it is the should not be so much difference that can scientifically affect our finding. So there are studies going on this one using different reanalysis product.
Yeah. There are no more questions from chat box. I have a small query, Dr. Sanjay. This Asian summer monsoon anticyclone one established in the same year, whether during the season will transform to Iranian mode to Tibetan mode?
In the same year, yes. Yeah, because this is because this is the convectively generated things. So that convection itself has this is the transient feature that actually 5 to 20 days actually oscillate. That means that there will be active and break phases, and during that actually it creates that the dominance of the either Tibetan mode or Iranian mode. So it depends on that's what we have seen here, that during active case we have more dominance of the Iranian mode. Okay. So that's what we have. Then again we have to see the convection and advection, how they play role in the actually yes.
Very good, Dr. Sanjay. Now we'll move on to the last talk of the session and for the day also. Now I invite Dr. Akhil Raj from NARL Gadanki, and he'll be presenting on defining the upper boundary of the Asian tropopause aerosol layer atoll using the static stability. Dr. Akhil Raj.
Thank you, sir.
Yeah, your slide is visible. You can go ahead. Yeah.
Good evening to all. Myself Akhil, a research associate at the National Atmospheric Research Laboratory, Gadangi. Today I am going to present few results we obtained during ISRO NASA sponsored balloon-borne measurement of Asian tropopause aerosol layer conducted during 2014-2020. And the title is Defining the Upper Boundary of the Asian Tropopause Aerosol Layer Using Static Stability. And we have collaboration with the US and Switzerland. So the previous two speakers have already elaborately discussed about the Asian ASMA and Tibetan anticyclone. So I'm directly entering to the ATAL, that is Asian Tropopause Aerosol Layer. The ATAL is discovered few years later to the discovery of the ASMA, that enhanced trace gases in the upper troposphere. So the ATAL is observed near the tropopause, and it's crossing the tropopause, and it's observed beyond the tropopause. And after that, there is a minimum observing. And here on left side, I'm showing this vertical cross section, and the down panel is showing the spatial variation. And here that it's crossing the tropopause, the 380 potential Kelvin is considered as the tropopause altitude, and beyond that it's a minimum. And again there is another layer, that is well-known stratospheric aerosol layer called Jungi layer. So what's separating these two layers? That is what we are discussing in this presentation. And the battle campaign, that is balloon measurement campaign for Asian tropopause aerosol layer, which is started with the three major goals, that is characterizing the optical, physical and chemical properties of ATAL, and impact of water vapor and ozone on ATAL, and the role of convection in the formation of ATAL. So this experiment conducted during 2014 to 20, and from three locations over India: Gadangi, Hyderabad, Varanasi, as shown here. And during this campaign, we have launched multiple instruments such as optical particle counter, microanemometer, and cloud particle sensor, etc. However, in this present study, I am using ozone zone, an instrument which measures ozone from surface to 30-35 km using an electrochemical cell. Another one is a cobalt. It's a compact optical backscatter aerosol detector, which have two channels. One is 940 nanometer and 455 nanometer. It gives the backscatter ratio, and the signal is detected by a photodiode. And we also used CFH, a cryogenic frost point hygrometer, which works on the principle of chilled mirror, and it gives the dew point temperature. From that, we calculate the water vapor mixing ratio and relative humidity over ice. And in addition to that, I have also used Calypso data for backscatter ratio from and also GPSRO Cosmic and ACFTS trace gases operation. And here left side shows the setup of balloon launching from Hyderabad. So in order to first address this ATAL, we have to find out the tropopause parameter. So we use the temperature profile on 1st August. It shows here the minimum temperature below 20 kilometers is identified the cold point tropopause, and lapside tropopause is identified using the WMO criteria. And again, the lapside minimum in the potential temperature is defined as the convective outflow height following the Mehta et al. 2008. And again, the one more tropopause parameter defined layer of maximum stability, followed by Sunil Kumar et al. And Gentleman and Wang. So this is the layer. Form as a consequence of the temperature shape of the temperature profile, which is basically because of radiative or dynamical process. And along with that, we have plotted here vertical profile of backscatter ratio obtained from 455 nanometer. So in this one, we both get aerosol and clouds information. And in conventional method, people used 940 nanometer less than 2 and color index, which is CI, which is a ratio of 940 nanometer and 450 nanometer, which is less than 7, and eye saturation less than 70% as a criteria for detecting the cloud and aerosol. So once this criteria comes, it is comes under aerosol. Later, Hanumandu et al. Introduced a new criteria, which is using only backscatter ratio at 455 nanometer, which when it comes below 1.12, it's considered as a aerosol, and anything above that is considered as cloud. So we have here multiple clouds, thin clouds. And we looked into the other station, Hyderabad and Varanasi also. So we can see that this profile, and ATAL is observed near to Trov Pass in both Varanasi and Hyderabad and Gadangi, and the minimum is observed near to the layer of maximum stability. So in order to make a climatological picture, we need to remove these clouds and this higher backscatter ratio. So we use WCT method to remove the clouds. So this is the WCT function, and this is the WCT step function shows here. The minimum and maximum of this step function shows the lower and upper limit of the clouds. So we removed these clouds and we got a smooth profile of the backscatter ratio at 455 nanometer. And this method applied to all the three stations, and we made a climatological picture of atoll from this backscatter ratio. So the atoll is observed near the Trov Pass or above the Trov Pass, and it reaches a minimum around Lmax, all the three locations. And this Lmax is observed around 1.7 to 2.7 kilometer above the CPH, that Cold Point Trov Pass, and it's found to be that the upper limit of the atoll. And the potential temperature at Lmax is around 440 Kelvin. And with a BSR or around 1.048, and this upper boundary is well matching with the concept of a forward Lagrangian model upward spiraling range. They have proposed that 460 Kelvin as the upper boundary, and our observation Lmax is showing 440 to 450 around Indian region. Similarly, they shown the lower boundary as 360 Kelvin, and the convective outflow level is matched with that altitude 350 to 358 around the Indian region. So Lmax is separating the Yungi layer and atoll. So what is happening means here more higher water vapor mixing ratio is available, and this previous observation already shown that the atoll is mostly found with small particles, and most of them are 80 to 95% are liquid particle. And when it's also some in situ formation is also happening, and simultaneously some aerosols are transported into the UTLS region. So both undergoes hygroscopic growth, and during this season the weak brevet Dobson circulations are persisting, and once the size started to grow and the gravity fall back to the upper troposphere, similar to the freeze drying of water vapor. And most of the and the Lmax also acting as a capping invasion, it will not further allow to go upward. So that's why the boundary is forming that altitude. So our water vapor observation from CFH also shows a enhanced water vapor in between Cold Point Trov Pass and layer of maximum stability. And same time, the ozone observation over Hyderabad also shows that a distinct feature near the Lmax. After that, it is increasing very rapidly. And we have an opportunity to look into the overshooting or the cloud unveil above Trov Pass on 18th August 2018. So the blue one is showing the backscatter ratio from the cobalt, and the magenta one is the water vapor mixing ratio. And the enlarged view is shown here, and we can see that on that day we have seen a water vapor mixing ratio around 5.68 ppmv in the above Trov Pass, and the cloud top which is reached around 17.6 kilometer, which is 400 meter above the Trov Pass. So we want to know how this broad view of the atoll. So we looked into the regional aspect of the atoll from the satellite observation. So here we plotted Calypso backscatter ratio along with the Trov Pass parameter from Cosmic GPSRO data. So we can see a minimum, the atoll is around Trov Pass altitude, it is beyond the Trov Pass, and the minimum is observed around the layer of maximum stability in both zonal and meridional mean thing. And we can see the Yungi layer well above this layer of maximum stability, and atoll below that layer of maximum stability. So both cobalt and Calypso observation able to distinguish that, and though we found that layer of maximum stability is the upper boundary of the atoll. So we want to look whether this is stand for the trace gases also. We taken the mean profile of trace gases in the atoll region, the ASMA region, 10 to 40 degree north and 0 to 120 degree north from the ACFTS data, and Trov Pass parameters are calculated from the Cosmic GPSRO during 2014 to 2018. So we found here it's carbon monoxide, water vapor, hydrogen cyanide, and ozone. And here we know none of these trace gases show any gradient near the Trov Pass altitude. However, we found that it's gradually decreasing and reaches a minimum or the typical stratospheric value near the layer of maximum stability. Similarly, tracer to tracer relationship between carbon monoxide and ozone also shows a very smooth transition. which is also indicating that some stratospheric mixing is happening in this region. And no, neither CPH or LRS, laterite tropopause or cold point tropopause, able to distinguish this stratosphere and troposphere in the ASMA region, both chemically and dynamically. So, however, we cannot conclude whether that LMAX is the upper boundary of ASMA, because the satellite data have very poor resolution. We have to look into high resolution in situ observation. Apart from that, chemistry plays major role here. In case of water vapor and aerosols, microphysical property is mainly contributing. So come to our conclusion, we found that in situ and satellite observation shows us maximum layer of stability as the upper boundary of atoll, which found 1.7 to 2.7 kilometer above the tropopause, and which separate the atoll and Jungi layer. And this the potential temperature is found at L maximum around 440 Kelvin over India, and over ASMA region around 450 Kelvin. And this concept is consistent with the proposed upward spiraling range within the ASMA by Lagrangian model. And a minimum value of backscatter ratio is found around 1.048 Lmax, and water vapor mixing ratio shows a secondary minimum near the Lmax, which shows the presence of lower stratospheric confirmed layer. And none of these trace gases shows a sharp gradient near the tropopause, which indicating that mixing in this stratosphere. But however, we need to get further details of chemistry to define whether the LMAX can be considered as the top of the ASMA. And I would like to acknowledge the NARL, ISRO, and NASA and TFR balloon facility, BHU, for helping conducting this experiment, and also acknowledging the satellite for providing this data. And I would like to thank Professor A. Jayaraman and Dr. T.D. Fleury for helping us realizing this project. Thank you.
Thank you, Dr. Akhil Raj, for a very nice and illuminating talk on upper boundary of the Asian tropopause aerosol layer. Now you defend a very innovative new definition for the upper layer of the atoll. Now the talk is open for questions. So there are no questions in the chat box. I have a question.
Yes, sir.
Akhil, now recently there was a very huge volcanic eruption, Tonga.
Yes, sir.
Did you seen anything signatures? I know that you are not conducted this experiment, but from the news or from the other observations.
Actually, from the news, when I was following, I found that it went through to this. It was in the southern hemisphere, and it went to the African region, as per my knowledge. I don't know whether it's reached to the atoll region. So, but in 2019, it was ended to atoll. So we didn't use those data. 2019, there was one volcanic eruption in the northern hemisphere, so it ended. And similarly, Canadian forest fire also ended. Those signals also we detected in 2017. So those data also we didn't use. After 15th August it was. So we didn't use that data. So current thing we didn't see.
Yeah. Hope you will be studying how these changes in upper boundary with the time will be affecting the radiative forcing, right?
Yes, sir. Yes, sir. We will be looking into different aspect. One will be coming the radiative forcing, so that in future.
Yeah. Thank you. Thank you very much. With this, we come to an end for this session. And I thank all the speakers for presenting their work within a time. And there are very new aspects of middle atmosphere as well as troposphere today presented in this session. I'm very happy to note that some of the very innovative and even first time we have seen the initial observations from DIAL from NARL. It was very nice to see that. Now we are coming to an end, and I thank Dr. Balasubramaniam for co-chairing this session. And I also thank LOC for their support, and they're always there. Whatever things are going wrong, they're taking back this thing to this operative things. I'm really thankful to them. Over to LOC.
Thank you, sir. With this, we come to the end of the third day for plenary session 2 on middle atmosphere, atmospheric coupling dynamics and climate change. We thank all the presenters for their engaging talks, and we especially thank all the moderators for this session, Dr. Kishore Kumar K, Dr. D. Balasubramaniam, Dr. Tarun Pant, and Dr. Nirvikar Dashora. Thank you again for this
Thank you, Dr.
session.
Kishore and Balasubramaniam sir, for nicely managing the session. Thank you, one and all.
Thank you. Good night to all. Yeah.
Yeah, thank you, sir.
Thank you all. Have a good evening.